Thank you. I'm going to kick things off. I know people are still getting back to their seats, but I want to keep us on time. So I will start this off with a little bit of background. I teach in the School of Architecture at the University of Southern California. I'm originally trained as an architect and studied building science at Berkeley before going into academia. But I am interested in growing the pipeline for building performance simulation, in part because I am responsible for educating the future workforce of building performance modelers. And you'll notice I'm here, I'm in California, and I'm at the CalBEM symposium. I'm using the term performance modeling rather than energy modeling, and I'll get into that for the reason for that, but I think that's critical if we're talking about growing the pipeline. And I'm gonna say, if we're imagining a pipe, I actually tried this because graphics are very important for me with presentations. I tried to find a suitable pipeline graphic for my presentation, and everything that came up just seemed inappropriate for energy efficiency. We did have some discussion of the natural gas pipelines and infrastructure here, but if you can imagine a pipe, then you have the sort of supply end, and then you have the end that's sort of meeting the demand. And we have, in building energy modeling, a huge opportunity here with the potential for all of this growth that's predicted to take place in over the next several decades. I'm going to just enlarge this a little bit so I can see it here. So this is an International Energy Agency projection that we are expected to see about 2.6 trillion square feet of new floor area added to the building stock by 2060. So I'm going out of this scale of California now to look at this in terms of the global projected growth. And then if we look at the goals for climate stabilization or mitigation efforts that are needed, we have you can sort of see here I guess the tan bars here, the activity is this growth adding to emissions. And then we have what's seen here as a projected mitigation effort that's largely driven by electrification and building energy efficiency. And then there are these other slivers like behavior, which I think would be really interesting to see how they made the assumptions for that. But the future, if we're going to achieve these climate stabilization goals, are going to have a lot to do with building energy efficiency and electrification more broadly. And it's going to be happening as much as this will be happening in California, it's happening worldwide, and much of the, if not all of the growth where modeling is applicable is going to be outside of this context of California. So I wanted to experiment with this future, and so being an architect, I had a home that was in a stage, a very kind of critical stage. If you reference back to Eric's presentation, much of the housing in Los Angeles was built in the post-war area, or the year or two right at sort of the end of the war. And so the home I was living in was in a terrible state and needed to be substantially retrofit and renovated. So I thought this is a great opportunity to make a entry into all electric living. So I performed a deep energy retrofit, did the performance modeling, and that you can see on the left here, this is the original gas service. And so at some point in the process, fortunately this was shut off before they did that. Someone took a saw and cut the gas service line, sort of was sitting like that for many months. And then over on the right is the circuit level submetering infrastructure that I was able to purchase relatively affordably, and have since collected over a year of circuit level submetering data to look at the performance of the project. And I'm starting to kind of get to terms with that. And what I found was that the annual energy use worked out to about 2.7 kilowatt hours per square foot for energy use intensity. And I thought, okay, wow, 2.7, like, I don't know what that means. Is that good? And so the first comparison I could make is to the performance model. So I looked at my performance model, thanks to CBEX Res. And I got into, and have since started to look at the sort of individual end uses in the model and do the end use comparisons and so forth. But overall, it was basically doing what the model was telling me. And the reasons, for the alignment were somewhat arbitrary, but it was doing a little better than what the model said. And what I learned about this was that you just met code, more or less, for this particular project, but for most retrofits, you could achieve massive energy savings relative to a median building in Los Angeles or a median building in my neighborhood. And I want to reference here, because it's not on the slide, that I didn't have any benchmarks when I was doing this. I had to go find the benchmarks for this comparison, and I found this tool online called the UCLA Energy Atlas, where I was able to look at various levels of granularity and see what the annual energy use for my neighborhood, for homes in my neighborhood, for homes in my city. And again, this is kind of an average across the existing stock. But if we could just say, if you can retrofit and you meet what the model says, you have this potential for significant energy savings. So I think it'd be very interesting to start to look into the ability to leverage that data in more detail and look at sort of time-based data or load shapes for those buildings and make those kinds of comparisons. But this was very useful for me to start to see how far we can get just with the existing expectations for energy codes. One of the things that I sort of neglected to mention with that project was that much of the work and much of the effort being trained as an architect was to rely on environmental services from natural systems. So the idea that this could be predominantly driven by a concept of thermal autonomy, so to rely on services from natural systems, natural ventilation, good envelope design, good solar control, and effective daylighting to avoid the need for electric lighting use throughout the day. And then, of course, combine that, the envelope upgrades, with high-efficiency heat pump equipment throughout the project to keep the overall energy use low. The problem is, and this is getting into the themes of AI, if we train AI models on the existing building stock or just business as usual practices, which have largely been, if we're thinking about modernism, been developed by projects that were built for sort of Northern European climates or climates that are space heating dominated. Much of the existing growth in the 21st century is going to be in climates that are much hotter, much more humid, and where the energy and resources are just not available to do these kinds of all-glass buildings or buildings that are not leveraging these systems. So I think as we start to envision what a future looks like, where we're handing off, sort of offloading the task of not only kind of predictive modeling, but the design of and execution of buildings to machines, we need to be very careful about what we're training those machines on, because the existing data or information about modern buildings is highly problematic as we translate that to warmer climates. On the flip side, for building performance simulators, there's huge opportunities here for employment. I felt obligated to do this, so I took the anticipated new construction by area, divided it by the number of members of a BIPSA, which was my only indicator other than BEMP certified professionals, and I calculated that we have about 456 million square feet of projects per member, and that works out to about 13 million square feet of modeling activity per member each year, which is a vast market for performance simulation. Now, the problem is very few or very limited number of projects actually apply building energy modeling during the design process. If we look at the number of building professionals, building modeling professionals that we need now, I thought it was worth looking at the overall employment for in the energy sector. So this is looking at total energy jobs in 2024 5.4% of all jobs in the United States, 2.4 million jobs in energy efficiency. If you just take the total number of architects and you assume you need about 1 modeler for every 20 architects, then it works pretty closely down to 180 new building performance simulation professionals per year, which then if you think we have 50 states, you divide that by 50, and then we have multiple universities. We're not really talking about educating a large number of new members of the workforce. So we have to find a way, given there's this huge growth opportunity, we have to find a way to get more of these projects, make the business case that performance modeling is essential for the success of those projects. AEC industry is one of the largest in the world, but it's one of the least digitized. Productivity is arguably in decline or stagnated, and it's an industry that's slow to adopt new technologies and practices. So this is a report, somewhat dated now, from the Department of Energy, where they're reporting that roughly 20% of new commercial and residential floor area applies building energy modeling. And again, this is just the energy modeling aspects of this. When we start to think about what we really want to see happen in modern buildings, if we're thinking about the energy outcomes, that's good, but really the key performance outcomes are the worker productivity, if it's a commercial building, or the health and well-being of building occupants if we're looking at more long-term performance outcomes. So how can we extend this idea of energy to a greater number of performance indicators? At the same time, and this comes from my immediate tasks starting next semester, is how to convince students that there will be jobs for them when they graduate that involve the kind of expected tedious tasks that early stage professionals are sort of exposed to as they begin their careers. And that involves sort of taking information from one location, trying to translate it into a different tool or workflow, and sort of, if you're thinking about conventional architecture, it would be drawing the plans and sort of managing that plan information. All of that is changing now down to the interfaces and the abilities to just simply have that done through translators and sort of eliminate these sort of early stage tasks. So this is going to be a very interesting semester, and I think it's going to be a very interesting CalBEM in that all of these, we can sort of expect all of this to change rapidly as we're confronted with the capacity of AI to do these tasks for us and thereby kind of offload all of this cognitive effort. And we, as educators, then are somewhat troubled by our, responsibility of actually educating and training students to be successful in these activities, where often it's the friction of doing this tedious work and identifying where things work and where they don't, and all of the challenges that ultimately drives the learning process. At the same time, California is encountering this kind of seismic shift in projected demand for electricity use, the introduction of data centers. This is one that has this is not being built in California, but a 2.2 gigawatt demand. And if you think of California's peak demand, you can sort of estimate, how many of these could be supported just with our current infrastructure. So where the focus will be on energy efficiency, on modeling, all of the different kinds of skills and abilities and needs and workforce that will be required to execute in a kind of effective way all of the efforts to mitigate those increases in demand for electricity. So, and again, in an effort to kind of provoke a conversation within the working group and within CalBEM today, I think that, going back to the pipe here, the first step is to grow the market, and that means expanding the value of performance modeling beyond where it's currently being applied, which is a fairly kind of narrow segment of new construction, to make the business case for performance modeling, and to begin to put more focus and energy into modeling what matters, which is the humans. I think with the discussions that have already occurred around the idea that models can be precise or that we can close the performance gap between anticipated or predicted outcomes and real measured outcomes, we have to understand that it's a false activity, because there's simply, we shouldn't expect when we're modeling or trying to predict human behavior, in a very, kind of specific ways, that we would get precise outcomes. And I can kind of validate that from my own experience with using compliance software and comparing that to measured outcomes. So at the same time, I think we need to leverage AI, and particularly new data sources, to learn more about how buildings are actually working once they're put into use. But we have we're sort of data deprived in the sense that we have this vast source of capacity now to generate and to produce simulated outcomes, but we still lack the basic infrastructure for buildings beyond just sort of baseline meter data. Very rarely do we have outcomes from buildings that speak to other factors that may be more important related to human factors or health outcomes. Okay, and then these are just a simple list of next steps to help grow the pipeline of performance modelers. First, we need to stabilize the employment landscape, and I think that's part of what CalBEM Working Group 2 is working on, to just sort of explain to prospective modelers looking at this as a career opportunity, that first, that those jobs exist, that they will exist in the next, in the coming several years as the workflows change substantially, what those look like in terms of economic viability. I also think there's a great opportunity to increase awareness at the K through 12 level, and I've been active in trying to find ways to introduce greater awareness of performance modeling in career technical education programs, increase pathways through architecture programs, obviously, and on and on. So I'll rather than read through all of these, I'll leave this for future discussion later in the day and in the working group session. Thank you. And it looks like that was right at about 20 minutes, so I have a minute or two for questions.
Hello, Gina Rada, Gable Energy. Can you go back one slide? Because you stopped right at the bullet point that I was most interested in, streamline, reduce cost of certification soup. Do you mind speaking to that a little bit?
Yeah, maybe it's a little provocative, but I think that it is challenging for early stage professionals to navigate the growing number of expected certifications, the annual cost of membership. One thing I like about CalBEM is it's actually free to attend. So as far as I could tell, you show up, you register online, you come here, you can participate. That's not the case for most organizations, right? They generate revenue through membership and through admissions and through costs for training materials and costs for exams and so on and so forth. And so that makes sense if you're affiliated with one organization, maybe two. But as more and more certifications, credentials, memberships, affiliations, and so forth, we need to create an option for students to engage with that, but also for early stage professionals to understand there's real costs and affordability questions that come up with that. And that's not to say that we have too many certifications, but it is an area that's increasingly hard for people coming into the profession to navigate. What should they prioritize? Any other bullets that looked good that I skipped over? Okay, thank you.
Thanks so much, Kyle. I love a provocative bullet. Awesome. Up next, we have towards BEMGPT, another maybe provocative statement. Fine-tuning large language models for building energy modeling education and training. Please welcome Liang Zhang.
Good morning, everyone. Let's talk about some AI. So today I'm going to talk about the BEMGPT, the fine-tuning large language model for BEM education training. So we'll talk about the background of generative AI and AI in BEM and also fine-tuning, and then how we develop the BEMGPT. Third, talk about the BEMGPT's performance and some discussion. Fourth, how we open source it. And finally, the conclusion and future work. So in the recent paper that published by Tianzhen and me, we listed several subsections of BEM that can be benefit from the generative AI or AI. So in the middle, we can see that generative AI or AI can really benefit the core modeling side. AI, including the machine learning and deep learning algorithms, can provide great data-driven modeling approaches as an alternative to physics-based BEM. But at the same time, it can be as an enhancement of BEM, especially using generative AI, where the large language model can help with facilitate the boring, tedious, or repetitive work that used to be has to be done by building engine modeler. But we also identified education and training is also very suitable, like subsection of BEM that it can be benefit from generative AI because of generative AI's nature of its ability of knowledge extraction, summary, which is the core of education and training. We thought about like 3 cases, but not limited to these 3 cases, use cases that Gen AI can benefit in BEM education and training. The first is interactive document and Q&A, which in this time, we don't need to have to look at each individual PDFs or search among multiple PDFs, but instead we can talk with it like we talk to ChatGPT or something like that. At the same time, there are a lot of like online forum like unmet hours, like where people will ask their real questions and some people will answer it. So it can also like extract this information, and also people can not search it online, but just talk to the chatbot to get these answers. The second is about training material generation. Generative AI can very easily create content tailored to different level of skill levels. And also it can tailor to different like BEM focus. BEM education has several like layers, like for example, the physics layer, teaching, especially in college, that you teach students what the heat transfer and how it works, how to energy plus solve the air heat balance equations. And also to the software layer, where you have to know how to use the software and also know its syntax. And then to the workflow layer, which is more widely happen in companies where you need to have your engineers to follow step-by-step procedures of modeling. So Gen AI can be very easily tailor this information into different skill level and application level. And also, nowadays there are text-to-video models like Sora. In the future, it also can generate training videos. The third potential use case is modeling tutor or like an AI assistant, where it can guide you through the simulation with instant feedbacks. It can help explain the errors to you and also explain the complex model logic to you, just like the programmers use GitHub Copilot and Cursor. It will do the same thing to Energy Modeler. Large language models, which is at the core of the generative AI, actually has huge opportunities in BEM education because it's very good at extract, understand, and summarize this domain knowledge or concept. And at the same time, a lot of technologies, especially the retrieval augmented generation, or RAG, further improves LLM's capability you can use some external data source and do the search and extract the similar information, relevant information to users' question, and feed into LLM together so they can get a better, more accurate answer with more truth grounding. But however, there are some challenges. The first one is cost. It's because nowadays models are getting bigger and bigger. The foundation models are large and always with more and more parameters to run, and it will be even more expensive if you're using some technologies like RAG, where you have to search relative information, and feed a super long token input with super long token. So it will make the whole process very expensive. And education is a process that a lot of students will ask a lot of similar questions. So if we repeat this kind of thing, the accumulated cost will be very high. The second is that we really need the model to need to reason and talk like a good BEM expert, not just retrieve knowledge, but really understand what's behind the knowledge. So that's what makes fine-tuning one of the important solution actually to these two challenges, where it focuses on like improving the small model to make it strong enough and smart enough to run cost effectively, even locally. And also can be taught to think and teach like BEM expert or educator. Fine-tuning is not a new technology. It's being widely used in the industry, and it has been very mature recently. Very mature and widely used. So the ChatGPT is the fine-tuned version of GPT model to make it more behave like a chatbot and to be more helpful, something like that. And the GitHub Copilot, the V1, is actually also fine-tuned from another GPT model by feeding it these kind of open source GitHub repositories and to learn it from the professional, these top programmers. So fine-tuning actually changes two sides of the model. It can give it additional knowledge. That's very straightforward. So it increases the knowledge of the model. But second, people usually neglect is that it changes also behavior. So it can make the response more consistently and also let it to be better at some capability like better at conversation or better at reasoning. So we developed our BEMGPT following this quite standard like procedures, which is not something we invented, but it's some standard procedures where we start with we need to find the foundation model to be trained on. So in this, to train BEMGPT, we use Llama 3.2 and Qwen 2.5. We tried these two models, which are widely used for fine-tuning. And in terms of the data, so because it's fine-tuning, you have to teach the model, base model, some additional information and knowledge. So that's why we select to use Eng+ documentations, including Eng+ engineering references, which focus on the physics behind the software and also the structures and the stuff behind the software. And also Eng+ input-output reference, which is more about the syntax and also some details in terms of modeling. And these are the raw data, but we'll have to convert it to the data that the model can recognize and to learn. So we do a data curation to make it to be a fine-tuning ready training data, which consists of two major data formats. One is text chunks, and second is question-answer pairs. So left side is the text chunks example, which is basically the original text from your PDFs or LaTeX format. And we chunk it to a right size to be not too long, so each training will be take too long, but not too short to split the meaning of different, because you wanted the chunks to have some consistent meaning. You're not suddenly just stop at a sentence where it has some correlation with the previous sentence. And the right side is our QA pairs. So we not only do the text chunks, but also generate the QA question-answer pairs from these chunks. And we use both of them to fine-tune the model. In terms of the algorithm, we use the supervised fine-tuning, or SFT, compared with reinforcement learning fine-tuning, which I will talk about later. And under the supervised fine-tuning, we use the PEFT, which is the parameter efficient fine-tuning, versus the full fine-tuning, where full fine-tuning is more like computation expensive because you need to change every single weight of your model. But PEFT is a more like lightweight way to fine-tune a model. And specifically, we use LoRa, QLoRa, and the dollar algorithms. And LoRa is the most standard PEFT. It's like add-on to a base model. So basically, your base model's weights don't change, but you're actually adding some add-ons to it, and you record that matrix and to work with that base model. So it's like a lightweight. QLoRa is something further better in terms of its reduced memory by quantize from 16-bit to 4-bit. And then DORA further improve its performance by using fewer training parameters. And since we actually try different algorithms, we try different data curation method. We also try different foundation models. And we try to find the one with the best performing combination. And the lines with the highlighted by the blue fonts are the parameter we choose for each part of the fine-tuning process. And we find that the Q1 2.57 billion is actually the best performing foundation model that we try among the 5 foundation models. Performance. So this is a comparison between the before fine-tuning and the after fine-tuning by asking some basic question about, okay, what's the 2 main types of loops in the HVAC simulation with Energy Plus? And before fine-tuning, you will observe this interesting thing is that it said the zone loop and the plant loop are the 2 loops. It looks right? But in Energy Plus, it's not called zone loop, it's called air loop. So, but after fine-tuning, you can see the results are more accurately captured, and also it adding more like explanations. Because the answer is too long, I'm just using a small portion of it, but it's not only detailed, but also accurate. And since there are all examples, so comprehensively speaking, the performance increased by 90% in terms of the burst score and also the other LRM-based grading. It actually improved its planning capability, which is ability before reasoning, is that we don't expect it to happen, but when we ask another question about what are the step-by-step procedures to build an energy model, which is something we want to test its planning capability or reasoning capability. And this kind of information has never been trained on. So you can see before fine-tuning is said, okay, first gather all the information, including this and that, and then it stops. It's not complete, and not following the instructions, like we said it be as detailed as possible, but it just stopped out there. But after fine-tuning, you can see it give a more structured answers about, okay, you need to have a detailed scope. You can define your scope, and then you need to gather building information, including geometry, whatever, and select simulation tool. Interestingly speaking, it said choosing Energy Plus because it's biased by our training, biased by our fine-tuning because it's fine-tuned based on the Energy Plus document. So it's actually improved its planning capability, but it's actually unfortunately biased by the thing we feed it to it. Some lessons we learned. From model side, we found the Qwen or Llama 3.2 are the very suitable ones. If you just look at the Hugging Face, you can see, if you want to know which one is better, you can just go to Hugging Face and see which model is being fine-tuned the most. You then use that one to do the fine-tuning. And then with the model getting, because these areas developing so fast, so the models are getting smaller and stronger, and which makes fine-tuning will be even better and cheaper. But downside is that if you want to have a new model, you have to redo everything. You have to retrain all the models. That will be somehow increase the cost. And we use Hugging Face Trainer as the platform, but there are many others like established and mature like infrastructures out there. One of them is Llama Factory and the others. And also we didn't actually reinforcement learning-based fine-tuning is also very widely used in the industry, and it's good for improve its reasoning capability, but in this study, we didn't try that. The lesson we learned from the data is that actually 90% of the labor hours are spent on data curation. You can see there are many ways that you can convert your raw data into. So there is include one, it's called CIQA, which is the context, instruction, question, and answer. Meaning that you have to prepare this like JSON-like format, like you have where you need to define what's the context of this information, what's your instruction, and what's the question and answer. But also you can using IQA, which is 3-element, QA, which question answer, what we use, 2-element, and text chunks, which is just 1 element without just only 1 element in that JSON-like the format. And we find that the text chunks plus QA pairs is better than the text chunks and also better than the QA pairs. This is because the text chunks are good at information completeness because you feed the whole text to it, you don't lose any information. QA pairs are good at actually capture the good questions, good important information. But the disadvantage is that if you have a paragraph, it's very hard to actually ask every single question to make sure the paragraph is complete. So merge them together will give you better fine-tuning result. The second thing is that we realized that our benchmarking, our testing is not fair to be very fair enough. It is because we are following a very standard machine learning and deep learning modern development method, is that using 70% or 60% as training, 20% as validation, 10% as testing. That meaning that our testing data is also all what we generated. The QA pairs is what we generated. But we cannot ensure that the quality of the QA pairs are right, because you have to have more building experts to actually to validate that. So meaning that we really need a good benchmarking in the BEM area to letting other fine-tuned models that everyone develop in the future to say whether it's accurate or not, good or not. The third thing I want to discuss, but I don't think I have enough time, is about the RAG, retrieve augmented generation versus fine-tuning. Since it's limited by time, if you have a question later, I can answer that later. But just very briefly introducing the comparison of them is that fine-tuning and RAG have their very distinct application. So, and I guess most of the time, actually, what you need to just using RAG will be enough, because currently sometimes cost will not be issued to you, and also you really cares about the accuracy of knowledge extraction. But the place where you use fine-tuning is the place where you really cares about the inference cost. For example, if you want to, for example, the Energy Plus in the future, if you want to have an embedded large language model in the future that is downloaded with the software and the user can actually run it locally, then you have to use the fine-tuning because of the cost. You want to run it locally. And in the place where you really need a good reasoning capability, use fine-tuning. But the fine-tuning and RAG are not like really competing each other. They also work with each other, because you can use your fine-tuned model to use as your your base LLM in your RAG to actually make it even better doing the RAG job to actually improve your performance further. So actually, we open source this BEMGPT by open source this model. It's fine-tune ready training data, and also the code for data curation and fine-tuning. So I also included in the last slide, so I will just move on to my conclusion. And the conclusion is that we developed BEMGPT, and we tried different algorithms, data curation method, and foundation model, and find the best performing combination. And I want to say that BEMGPT is not a fine-tuning model, but a type of fine-tuned model specialized for BEM, so everyone can develop their own. And what we want to do is just want to jumpstart the fine-tuning in the context of BEM. But just a suggestion that before you do that, you really think before you build yours, because it will be much more engineering, have high engineering cost than the RAG, is for sure. And only build it when it's necessary, if you really cares about the inference cost and also the reasoning capability. And the third I want to mention is that, we develop on the Energy Plus documentation, but a more knowledge base can be included more in your own personal, like BEMGPT, like other textbooks, other software's documentation, some online resources, like BEM Encyclopedia, and also more designer data, which included the chain, like for example, the chain of thought data from BEM expert, where you can interview these or getting this knowledge from really top modelers to get their knowledge and convert it to a fine-tuned data to be fed into the model. Finally, so it really it will advance the BEM education and the training in terms of this kind of support interactive learning with the software, and also behave and reason and think like a building edge modeler or educator. At the same time, with your fine-tuned model, it can also work with RAG, and also, which we talk about a lot, the agents, which they call it 2025 is the year of the agent. So you can also use it as the core of LLM agent to actually using RAG to access more external data, and also use agent to deal with more complex BEM education scenarios. Okay, so thank you for your attention, and look forward to your questions.
Hi, my question was on RAG versus fine-tuning. Could you go back to that slide where you compared the two? I was just curious. I think a lot of the projects that would potentially come out of this room might not have the resources for fine-tuning. I just wanted to better understand the performance trade-offs. I can't tell from that graph if you're saying that fine-tuning essentially results in a more accurate output from the LLM. And also, I wanted to understand the differences between the timing and that being agile. Like you mentioned, there's new models coming out all the time, and if you're going to use fine-tuning, you may not be able to jump from model to model as quickly. So just speaking from a perspective of being agile with limited funding, what might you recommend, or what are the trade-offs?
I would say most of the time, maybe 80% of the time, you need a RAG. Because RAG, you can see it actually separates the data with model. It's quite independent. So they are not like fine-tuning. You have to bake your data into a model. And if whichever one updates, you need to update your model. Either your knowledge base updated or your model updated. You need to redo everything about fine-tuning. But fine-tuning itself is very computationally expensive, relatively speaking. You can use a server, but in our lab, we use 2 H100 GPUs. And just fine-tuning these 2 documents costs us about 8 hours for each iteration. So I guess not everyone has H100 GPUs, but if you use cloud service, it'll also be expensive. But a RAG is you put everything outside of the model, and every time you retrieve relevant information to work with the question you have and feed it into the model and to work. You can update your data very easily. And then you can also say, oh, tomorrow I don't want to use Qwen, I want to use Llama. Then you just replace your base model. So it's very flexible and modularized, and also it's more accurate, comparatively speaking, because it's traceable. And also it's traceable because in fine-tuning, everything is merged into a model. They become a parameter, and it's hard to really. How to say, have some physical meaning or having some debug, this kind of thing. So that's why a lot of, if you a lot of people from the AI side or for the startup, they said, okay, for startup companies, please do not do fine-tuning, so it will ruin your company. So it will, because you cannot afford, because the knowledge base is updating so fast, model is updating so fast, please don't do that. So that's why they say fine-tuning will be boomed when the foundation model starts to slow its process. And at that time, you also have a lot of knowledge base ready. So at that time, then you aggregate this knowledge and then go use the relatively steadily performed models, and it will be the very great time to use fine-tuning. Did I answer your question?
Yeah.
Okay.
That answers.
Is there a reason that you went with using Qwen and Llama beyond the fact that they're the 2 open source models?
That's a good question. So we just do a trial and error process, and we just we tried actually because relatively speaking, Llama 3.2 are most widely used if you look at the Hugging Face repository. It's more so first, we are not super AI expert, that real people doing that foundational work, foundation model work. So we only use the ones that prove to be correct, right, in many applications. So the Llama 3.3 is really, 3.2 is a really good version, but no Llama 4. Llama 4 is actually kind of going, I don't know why, but the industry feedback is that Llama 4 is not good as before. So we use Llama 3, and the Qwen is just because it's, I would say, just widely used, we observe. And you can see we also tried a different version of the model, like 11 billion, 3 billion, 1 billion. So the reason we tried a different parameter is because we just want to see, because for some cases, if the model is small enough, it's easier to learn new knowledge because it's not smart, it's not that smart, and your new training data, comparatively speaking, is a lot to these smaller models. So smaller version of model may be more easily to be trained. So that according to the concern, we just try different version of models, like 7 billion, 14 billion, so this kind of thing. So we don't do a very comprehensive search for every single foundation model out there. because it's also expensive, like we said. We can't afford each model like 8 hours. If you try on 100, it will be very time consuming. So I would say, because they are they are very compatible with each other. Like, if you go to the fine-tuning infrastructure, actually it's compatible to a lot of current foundation models. So I would say I would just leave, people just can try their favorite, yeah.
Awesome. That wasn't controversial at all. That was fascinating. It's been really fun over the last 3 years of CalBEM, seeing the discussions around AI transition from, what is this? Weird. What could this mean for BEM? To what are we seeing coming out? To now participants developing things and sharing their findings and methodologies with the group. So thank you so much. Up next, we have our very own Nikhil Kapur, who is going to talk about the California compliance software updates for 2025. Nikhil?
Morning, everyone. Yeah, I'm going to take a detour from the future to the present. I'll be just giving a quick update on the 2025 California building compliance software, known as CBEC to most of you, I guess. Just highlighting where we are in the energy code for 2025. We are at the tail end. The implementation starts in another month and a half, I would say, at this point. And then most of the development work and everything has happened. And now we are in the implementation phase, both on the modeling side and the compliance side. Compliance side as well. So where we are with the 2025 compliance software. Through the year, we've been doing some release versions, research versions for public to comment on. We've kind of put out a couple of release candidates in April and May. And then we also adopted the 2025 ACM manual, which was approved in June, which led to the release of the 2025 1.0 software. We just released the latest version, the 2025 2.0 CBEC software, which decertifies the previous 2025 1.0 software and is based on the latest ACM approval as well. As we proceed towards the end of the year and implementation date of January 2026, we will also be doing the third-party approvals as they come in. This slide just gives you a high-level update of the software updates. We are basically updating the 2025 2.0 to the ACM rules that were approved in the October business meeting. One of the things that we did do with this 2025 2.0 update, which also led to the decertification of the 1.0, is that we did the unification of the modeling for single family, multifamily, and non-residential all under one hood. So you don't have to install two programs separately. They still function independently as they used to function before, but at the very least, what we did was take the first step of unification in terms of the interface. So you can just install one program and load any software, any building model that you had previously. The other upgrade that we did was to the latest version of Energy Plus, 25 1.0. I know 25 2.0 is already on the way, but we'll be looking at that, in the year or next to see if we need to upgrade it. But I think we got all the capabilities that we needed with this upgrade as well. Some of the software highlights, the unification I've already kind of highlighted on. We are also extended the support for the executive order that was passed for the LA fires and the PV battery exemption, so that will be included in the 2025 software. On the non-residential side, a couple of capabilities. We added a new air-to-water heat pump model. The air-to-water heat pump model that we had previously used the water heater object in Energy Plus, but now we have a dedicated plant object that we are using. Thanks to the stakeholders and the case teams and all the folks who do work here, we have removed tailored lighting method. That was part of the compliance improvement, so that's no longer supported in the software. Previous versions do support it. And then the other updates are related to ventilation updates and common area lighting updates, as part of the code update, are included in the non-residential software. On the single-family side, there has been a change to the modeling of the unitary AC and heat pump modeling, the variable heat capacity heat pumps. A new algorithm has been introduced, details of which will follow. And then based on the code update, now we have a dual heat pump standard design in all climate zones as well. The other major shift in the single-family metric is that we are switching from EDR to long-term system costs, LSC source, and then a new metric called the peak cooling metric, which you can get details from the CEC website as well. In addition to this, we've made improvements to the NRCC, the compliance reporting forms as well. We continue to improve those, so we got as much as we could in this round, and we'll keep improving upon those as we move forward. So just talking briefly about the unified user interface, like I said, no changes to the user experience once they load a file, but the only change is, not juggling between two separate programs for single family, multifamily, and non-residential. One of the other improvements we are looking at a combined sort of a quick start guide and release notes. We'll be improving upon that as we move forward with the combined interface. And then also work is underway, planned for combining the ACM reference manuals for the res ACM manual and the non-res ACM manual previously into one ACM reference manual, and similarly for the user manual as well. This is the new air-to-water heat pump object that we introduced with the Energy Plus upgrade. The object is called air-to-water heat pump EIR. It is being used as in the standard design wherever the multi-zone requirement is there as per the ACM update. One of the things we are hoping to do is use this object further and develop its capability for the cooling side as well, and in heat recovery. There is some work underway by the stakeholders to look at this object a little bit more closely and get those capabilities into the software as well. The single-family residential modeling for the unitary AC and heat pump modeling, we are supporting a new modeling algorithm, which is based on ResNet publication 0325. If you want details on that, you can, get a hold of Neil Cruz here. He's somewhere in the room. But that replaces the previous, single-speed AC modeling method and the VCHP modeling compliance option. I know we've been getting a lot of questions regarding that. Earlier, that compliance option existed because we were not able to capture the modeling of it, and there were some credits associated with it in 2025. Now, since we can model it, you can see that there's a drop-down there. You can choose between a variable speed and a constant speed. That modeling option is no longer available in 2025. Another thing that we are carrying over from 2022 is the executive order that suspends the PV and battery requirements in the residential structures impacted by the LA fires. Once these boxes are checked, the PV requirements will not be simulated both for the standard and the proposed design. Another update, we've kind of done an automatic exception checkbox in CBEC, so you can check the box and it'll automatically apply the PV exceptions. The other update that's happening on the PV side is that the single-family standard design PV, which used to be a simulation on its own, sizing simulation, is now directly based on the prescriptive requirements from the code itself. So there will be no more sizing run for the PV. Reporting updates, there are some structural updates. There are some updates to just reporting of elements. We worked through with the SMEs and the stakeholders to get as much as we could for the CF1Rs, that's the single family, and for the NRCC and the LMCCs, and we are continuing to improve upon that as we move forward. Another important thing, which doesn't relate to code compliance directly, but we have incorporated the California Utility Allowance Calculator. It is now available for the single family projects as well, and we are continuing to enhance it through stakeholder feedback. One of the things we have introduced is a combination tool, so it can combine reports from various projects together and present as one report. And then, the rate updates are also included in the 2025 2.0. And as we move forward into the next year, we'll be looking at ways to improve the QAC calculator as well. It does run its own simulation and its own reporting, which is not tied to the reporting server. It's the locally reporting, but it doesn't do code compliance. So I just want to point that out. I won't be delving too much into the metric updates, but like I said, all the metric updates have been updated to reflect the latest code. We are moving from time-dependent valuation to long-term system cost. I believe there's a presentation later today or tomorrow by E3 on that as well. There is some cleanup on the single family where we are moving away from the energy design rating to the LSC and source, aligning with the non-residential and multifamily. And then, of course, a new cooling metric for the single family multi-residential. This is just summarizing the metrics on the various scopes. The peak cooling is only applicable for certain climate zones and for certain times of the day through the months from July through November. Some current and future software work. I know there's a lot of been talk about AI. I don't have a bullet for AI here. That's something we'll be observing and seeing where the industry is headed. I think there are a lot of sessions happening today, so nothing on there. But we did do a major milestone. Noresco helped us move our repositories from SourceForge to GitHub. So we now have a home on GitHub. That's the address for the current repository. Our final repository destination is going to be on the California Energy Commission GitHub site. So we'll be working on that in the months to come. Another couple of things that are happening simultaneously. On the code side, there are executive director approvals for multi-zone heat pump alternatives that have been worked on by various groups. So that's something we're looking forward to. Third-party software approvals as applications are received for compliance, starting 2026. Third-party softwares will also be available for compliance, code compliance performance runs. And then again, we'll be working on more UI and reporting up enhancements with the combined UI as well. For 2028, there's already work underway. So we will be releasing a version of the software with the 2028 LSCs and source metrics, which is coming soon after as well. And then there are proposed updates to various code updates and case work that's happening on the LSC, the source metrics, and the welding prototypes. I believe there's going to be more talk about these in the working group sessions as well. These are just some of the resources you can link to and get more information on the code itself and the compliance software updates. We continue to support the user support through the email addresses right now. CBEC for non-residential multifamily and CBEC Res for single family. This is something we'll be working on to consolidate in the year to come, and also looking forward to some updates on the code repository to come up with a wiki and FAQs where we can host most questions regarding the modeling for the compliance software. So that's the update on the 2025 software. Welcome any questions.
Hey, Nikhil, I've a few questions. I'll try and catch you in the corridor for, but a couple of quick ones. You mentioned 2025 new features. Do you anticipate any of those requiring a third-party recertification?
The new I don't believe so. So everything, whatever is included in the ACM. So all we did was we switched the air-to-water heat pump model to a newer model, so it'll have new performance curves. So if you're already incorporating those performance curves, then there's no recertification there. But 1.0 has been decertified. So if you are basing it on 1.0, then we'll have to recertify for those.
And in calendar year 2026, 27, any new features will not require a recertification?
So it totally will depend upon the ACM. If they affect the standard design and the previous version is being decertified, then it will require. But with the updates, there will be recertification for features if you want to incorporate. So we will be adding those in. The process will be the same as the previous years. So there's no change in the process there.
Okay. And you mentioned Energy Plus 25.1.0. Is that going to stay the same for the entire duration of the code cycle?
That's a good question. We usually don't change Energy Plus versions that often unless a major bug has been found or some capabilities that have now come in 25.2 or beyond that are really needed by the industry for the proposed design. So I don't see changing 25.1 from 25.1.0 to 25.2.0 soon, but we have done changes, and at that point we will be decertifying the previous version. What that means is that projects that have already gone into permitting with the previous version will continue to use that software, but any projects coming in for new certification that haven't gone for permitting will be using the new version.
Thank you.
Hi, Nikhil. I'm here.
Oh,
hello.
Sorry.
Thank you for the update. There's a couple of quick questions. On your unified software, just to be sure, for the residential, we're still using CSC with all these features on the condition zone, and so we're not changing any of that.
That is correct.
And then the second question is on the utility cost calculator. So all the utility rates are in there, so depending on the climate zone, whether we're in SMUD, PG&E, ESC, all of that will be loaded, and that can be used to calculate the energy cost. Is that?
Yeah, that's specific to the compliance utility allowance calculator. It doesn't work with the code compliance runs. So, and then that's specific to those projects that are using the QAC for the TCAC submittals for the affordable housing. So the utility costs, the utility rate database behind the scenes, is not accessible right now. So that's something we'll be looking at in the future version to see how accessible we can make it. So.
Thank you.
Jim Lutz here, and I've got a water heater question that has been bugging me for a while, and actually I've had some conversations already. The manufacturers of water heaters are coming out with new brands and new models of heat pump water heaters faster than they can get included into the CBEC res. How do we go about speeding up that process? Who should we talk to figure out how to get the manufacturers to help support that and get the modeling tools we need and all that? Who at the CEC should we be?
So you'll be contacting me and the tools team essentially. For those updates. I know the manufacturers are coming up faster than we release the softwares. We are looking into ways to improve that. We are also looking at ways to make generic options available that would fit in the class of those water heaters, but with their performance characteristics, so that you could enter the performance characteristics and not have a model number listed. So there are various ways we are looking into improving that. As far as releases go, if in a month somebody releases 10 new water heaters, we are not going to come out with the software immediately. So that will be on a certain schedule. So we are looking at ways how we can improve that thing, to include these water heaters and come out with it. But I think we are also looking at generic options that might give you a capability where, okay, I know this manufacturer has this efficiency, and we can use that to do that. I know Big Ladder has been working on some of that work, so you can contact Neil Cruz here on the residential side.
Yeah, thank you. I'd like to shed some additional light onto what Jim just said with regards to manufacturers coming out with new products. Yes, we are coming out with products much faster than the software can accommodate. But from our perspective, one of the big challenges with this software is there is no scheduled updates. So as a manufacturer, we release a product, we have an expected release date, but We don't know when that product is going to make it in the software. So to put an example out there, Bradford White released a new Aerotherm G2 in July. We provided the Energy Commission and associated partners with data for modeling in May. We still don't have a model. We don't know when we will have a model in CBEC, and therefore we cannot even sell our new product in new construction until when? 6 months after release, 8 months after release, 10 months after release. So we're requesting that we would like to see a scheduled release date for software. I mean, frankly, preferably once a month or every other month to accommodate new models. We want to know when we have to submit data in order to be included in the next release. There's none of that information available. It is a black box that we are just sort of operating at the whim of the Energy Commission and the associated consultants who are building this model. The alternative solution I would propose is to do away with individual makes and models and use the current generic tiered system of NEA and Uniform Energy Factor. Then we would not have this problem, and then we can work with the current software release schedule and the associated consultants to refine the generic models to make them better as new products are added in and more data collected. That would be the simple solution, but right now the solution that is currently available is completely unworkable for manufacturers and puts us at an extreme disadvantage to sell our products in the state of California.
No, I agree. That's something we are trying to streamline in terms of schedule. So now with the moving of our repositories to the GitHub, we are also trying to see if we can have some sort of an update that's available when in cadence we are going to be releasing a software. In terms of the generic water heater option that you just mentioned, that's something also we are looking at. We also want to make sure that there's a lot of work that goes in. Once a manufacturer gets it to the consultants, then they have to evaluate it, then they have to create the algorithms for it, and then we have to get it into the software, and then we have to release the software, test and release the software. So one of the things is we are looking at the generic option a little bit more. This problem, I think, exists on the residential side. On the non-res side, we always had the generic option. So we didn't have to kind of figure out like, okay, you have a higher efficiency, you just put the higher efficiency in there. So that's something we will be discussing on what cadence can we get the manufacturers to give it to us, and then what we can incorporate in the next release. We would like to move away from individual water heaters. I know initially it was the industry adoption that this came in for, but that's something we are still discussing and seeing how we can make it much faster.
Nikhil, just to help follow up on both of these questions, I'm going to be presenting tomorrow in a session on the future of heat pump water heater modeling, and part of the presentation we'll get to both of those questions directly in a proposal that I'm providing for the commission as well.
Okay, thank you.
Thank you so much. Up next, I'd like to welcome Mudit Saxena, who will be presenting on equitable home energy labeling at scale. We've had talks from Mudit before, and every time there's an update with insights, we're really grateful. So thank you.
Hello, everyone. Thank you for having me. My name is Mudit Saxena. I'm the CEO and founder of XeroHome, and it's a pleasure to talk to you about the role of building energy modeling in home energy rating and labeling. Quick acknowledgement that the analysis that I'm presenting here today was funded by Southern California Edison's Codes and Standards program on the request of the Energy Commission, and the analysis was done by our team at XeroHome as well as with 2050 partners. So California is a very diverse state with lots of buildings, 14.2 million homes, 9 million of those are single-family homes. Each home uses a different utility rate, it's built differently, it's in a different climate zone, so uses energy very differently. The challenge that the state had is how do we build an energy rating and labeling program that works for all homes, right? So this is the challenge that the California Energy Commission is currently sort of working on. And the way we started to sort of think about this is that one very important thing to consider when you're putting up a program for a state that's diverse is that any rating or labeling system that we come up with must work for everyone and not leave anyone behind. There are homes that are in disadvantaged communities, there are homes that are rural, and there are homes that are not. And any kind of if the rating or labeling system creates any kind of entry of barrier to one of these homes, then we're not doing the right thing. We're leaving someone behind. And that's really important because we need these homes to participate. So if there's a cost to labeling or rating your home, that immediately puts up a barrier for one of these homes. So what we really want is the energy label should be available for every home. It should be equally available for everyone. And to be able to do that, what we really need is something that's universal and it's free for the homeowner, right? It should be available for everybody to participate in. And to California Energy Commission's credit, that is exactly the way that they've been thinking about this as well. So when you think about how do you put together a rating system that's available to everybody and it's available and universal, one of the first thoughts that come to mind is that you could do this using home energy data, right? You have meter data for every home. Why don't we just use that to build an energy rating system? Well, when we start to unpack that, you'll start to see the problem with this, which is, you've got two homes that could have the same energy usage. You have a large home built to the latest energy code in California versus a smaller home built in the 1970s, perhaps, and they will have the same energy usage totals, right? So the energy rating will not be able to differentiate between these two homes, and that's a problem because one of the basic necessities of this rating is that you need to be able to inform the homeowner exactly what they can do to upgrade that home. So that's a problem. Secondly, if you look at energy usage data, along with the data comes behavior and variability because of weather. So from year to year, the energy usage of a home can change quite drastically based on the occupant in the house or the weather on that year. And that's going to distort the results if you base an energy rating and labeling system purely on energy usage data alone, right? So usage, not the same as efficiency. So the second thought is, why can't we use all of this advancements that we have with AI, with natural language models? We had a great presentation that kind of talked about that a little bit. Why can't if we throw all of this energy data into a large language model, perhaps it can just churn out a really great energy labeling system for us. Again, if you start to unpack this a little bit, which is how we approach this also, you realize that an AI model that would just take in energy data and output a label will not be able to give you any insights, will not be able to give you any explanation. So if you get a rating out of that system that we might build, it won't be able to give you any understanding. Whereas on the other side, if you have a physics-based model, which is what we have with LLMs, with BEM, you would be able to query that model and kind of get some understanding of the physics of why you're getting a rating that you're getting. So again, sort of thinking through this the AI models tend to be black boxes, right? They are designed as a black box. You can't quite see what's happening inside. So just having usage data thrown in and label come out may not be kind of the most appropriate use case for AI for this particular matter. The other thing is that even if you were to go in that direction and build something like this, you'd have to train that data. You have to train that model on some data. And there's something called the data burden, which is you have to tag that data. And sometimes that has to be done at a large scale in a very, it's a labor-intensive process. So where would we even start to even tag such large information? So that's not a trivial matter. And I already talked about sort of the missing physics in these models. So the conclusion that we kind of reached was that AI can really find patterns, but physics can explain the data. So for this particular use case, which is creating a rating and labeling system for homes at scale, building energy modeling seemed like a more appropriate way because it gives you sort of an asset-based rating of a home, not a behavior-based rating which would come from energy usage data. So the path that we kind of proposed here is, which is we consider as a more scalable and equitable path, would create a building energy model based off of publicly available data sets. So we're able to take access to all of these public data sets. We had a great presentation at the keynote about that as well. GIS shapes and data files can be used to build geometry. Tax assessor data, building permits data can be accessed. MLS data can be accessed. And you're going to build all that. You can synthesize that information, and using cloud compute, you can kind of build these energy models at scale. And you don't have to send somebody over to a home to be able to build the first layer of that model. Like, you can build that first level model without doing any legwork on the house itself. You can get all this data remotely. And then you can turn to the energy usage data and add that to the equation and calibrate those energy models based off the energy data that you've now acquired. And using those two pieces together, you will have what we call a calibrated energy model, which will be a very powerful resource to be able to give advice to the homeowner on what they can do about their home, but also churn out a rating or a label for that home. So at my company, XeroHome, we kind of use this approach to build a tool. It's called XeroHome. And so we've been able to deploy this tool in the last 7 years that we've been in business in multiple locations throughout the state of California and a few outside as well. And we've had the great opportunity to have this funded by some of the utilities here in California, as well as outside. And so now we have data around this approach, which I'm going to present today, to kind of show you exactly what we are seeing in terms of the accuracy of this approach and whether that's a feasible way of thinking about an energy rating and labeling system for California. So the rest of my slides are going to be about the data. So we're going to talk about sort of the idea here is to be able to demonstrate a feasibility of a no cost to the user or the participant statewide rating system that is feasible to implement, accurate in its results, and scalable across millions of homes. So what we've been able to show through the last 7 years of deployment of the tool XeroHome is that it is feasible. We've been able to build a tool, and it's scalable because you're not sending somebody to your home to collect the data. We are actually able to build these energy models remotely. So it is both scalable and it's feasible. The last question is of accuracy, which is kind of going to be the rest of my slides today. So we'll talk a little bit about what we've collected and we've been able to analyze about accuracy. So before I talk about the accuracy and show you actual data from our deployments, I wanted to sort of set the stage for what I mean by accuracy and the metrics that we're going to use. So we came up with this metric called calibration coefficient. So if you take the energy usage of a home and you divide it by the modeled energy usage of that home, you get this ratio. If it's a perfect model, you're going to get a ratio of 1. So what you're shooting for is a calibration coefficient of 1. If it's more than 1, then there's a bias, or less than 1, there's a bias on one or the other side. It's overestimating or underestimating. So if you do this for thousands of homes, millions of homes, and then you can create a histogram which should look kind of like that. You'll have a bell curve which peaks at 1. That's what you want to see. Now, if you see this bell curve shifted to the right, that means the models are underestimating, right? So there's a bias in the model. And if you see that the bell curve is pretty flat and it's got a very long tail or tails, then there's a lot of uncertainty in the model. There's some that's under-predicting, some that's over-predicting. So what you really want to see is a bell curve that's close to 1 on its median and not very long tails, right? So that's kind of the goal that we were shooting for. So now next slide is about the data. So the hypothesis is that adding energy usage data to an energy model that was built using publicly available data will actually improve the model's accuracy. So let me show you the first example of this, which is Climate Zone 12, which is our climate zone here in Sacramento. This is the city of Sacramento. This is data that we worked with the city and with SMUD with. And what we've got is a histogram that comes out of our first layer models. That's the models built with publicly available data only, right? So no energy data yet. These have not been calibrated. So what you can see here is that you've got a histogram. The green line is a target for the median. It's shifted. It has a bias. Our models were underestimating energy usage, right? And you do see some long tails with a very long tail greater than 3. So right off the bat, we were saying, okay, the models weren't doing a great job of predicting actual consumption. So then next thing we did is we said, well, let's get energy data and calibrate these energy models, and can we do a better job with that? This is with the energy data added. This is with the calibrated, now we've calibrated the energy models. Now you can see that the median has come much closer to that target. It's almost at 1. And also the standard deviation, which is the measure of the spread of this data, has reduced from 1.05 to 0.8 about, right? So both in the right direction. So we've got a much better fit of these models. So remember, these are about 100,000 homes that I'm showing you here. We haven't been to any of these homes. We haven't entered any of these homes. We haven't asked any questions. We're just using this remotely, and we're able to get quite good with the energy data itself. So that's example number 1. I'll move on to example number 2. This is from Southern California Edison's regions, one of the cities we modeled there. This is climate zone 9, a much milder climate zone. And you can see that already, even without energy data, we got pretty good. We got pretty good agreement with usage. The median was standing right at 1.07. And the standard deviation was about 0.7. So we were pretty good just to begin with. And why is it that we got good agreement in climate zone 9, but we're not climate zone 12? Well, we did a few other climate zones as well with PG&E, and those were coastal climate zones too, and we kind of replicated the same thing, which is in our milder climate zones, the energy models based off of public data are actually doing a pretty good job already. So what we're seeing here is 2 things, right? One is we're building these models using public data. So one is the public data is quite reliable. That's good. Number 2, the methods that we're using to model are also quite reliable. And what are the methods we're using? It's the California Energy Commission's ACM process of building a model. It is the NREL's Building America simulation protocols that we're using to build these models. So this is really that showing up in actual data, and we're able to see that if we follow those processes and we do a diligent job of building these models correctly, they will agree with energy usage data. And sometimes you have to use calibration, sometimes you may not need it. So that's example number 2. So our hypothesis conclusion was that yes, energy data was definitely useful. We had a second hypothesis, which was if you don't want to send an energy assessor, because that costs and access to energy assessors is not always there for rural homes, for example, can the homeowner kind of play proxy? Can we ask the homeowner some questions about their home, and can that input then be used in our energy models, just like we did calibration? Can we use those inputs to tweak those energy models for those homes? And will that change the accuracy of the models too? So I have some data around that. So we did that. So in XeroHome, we have a web-based tool. So it allows the homeowner to type in their home address. And we have a set of 16 questions that they can optionally answer. So it's a mixed bag because the questionnaire has been designed to be useful. So you can answer 1, 2, all 16, 5. You can kind of skip the questionnaire wherever you want. And also, we don't have every homeowner coming onto the platform once we deploy a tool. So the histograms you're going to see here are less bell curvy, if that's a term, because the N is smaller, right? So you can already see kind of where the issues may be. So on the left is without homeowner input, and on the right is with homeowner input. Now, on the charts itself, you can't quite discern the pattern. But if you look at the numbers, the movement is in the right direction. The bias did reduce by about 30%, 39%. And there was some movement on the uncertainty as well. The standard deviation went down. So yes, we don't have a lot of data on this yet, and we are collecting more information as we deploy the tool more. And as we process more of that information, this bell curve can be a little bit more understandable. But what we are seeing is the movement is in the right direction. With homeowner input, you are getting better at agreeing with energy usage. Climate Zone 9 deployment, we had more data here, about 459 homeowners answered questions. Didn't see a whole lot of movement. Again, this is Climate Zone 9, we were already pretty good, and the homeowner input, again, sort of made the move in the right direction, but not a very big change, but still in the right direction. So key takeaways were that both energy usage data and homeowner inputs added to this large-scale energy modeling process were giving us very good data. And in the interest of time and some questions, I'll stop here. I have a couple more slides that talk about variability. So if you look at these graphs and you still see tails on those, and you wonder what those tails are, well, you're never going to get an exact match to actual energy usage data because there's variability. Let me just quickly go through these. So there's variance in terms of weather, like the jaggedness of those lines essentially showing last 100 years of climate data. It shows you that every year your climate can change, right? And so you're going to have differences. When we model to a typical meteorological year, TMY file, right? Not an actual meteorological year. So when you model to that, you do get some variance because of that. There's also variance because of behavior, like homeowners' preferences, thermostat set points, for example, are going to move this thing quite a bit. So there's things that you can kind of control for, but you're not going to get exact matches for. And so any histogram that we create is still going to have those tails. So that's that. I'll leave you with the conclusion slide. So we have some time for questions. I'm sorry, I kind of took a little bit longer than I anticipated. But those are our conclusions that you can read, but I'll open it up for questions. Thank you.
Two quick questions. One clarifying question. So when you're talking about the energy consumption data that you're using for calibration, is it both electricity and gas, or just electricity?
Yeah, depending upon which project, sometimes we had both electricity and gas, and sometimes we had just gas.
I'm just wondering if there's any, you're doing a better job predicting one or the other. Is that?
Yeah, interestingly, what we found was that the gas data we were doing a pretty good job with. Not a big spread on that. The electric we were doing a worse job on, and a lot of that has to do with miscellaneous loads that electricity has, and gas is more predictable. So even when we didn't have gas data in a few of our projects, we were okay with just electric energy calibration. But when we did have gas, we did calibrate to it.
And then just quickly, have you been looking for structure in the error? So basically, like, are there patterns in terms of the shared characteristics of the households that you don't do as good a job predicting in? What might those be? Are it higher consumers, lower consumers, things like that? I mean, is that part of your purview? Or?
Yep, we started looking into that, but not a pattern didn't quite emerge from our first initial looking at it, but there's more work to be done there for sure. Yep.
Hi, thanks. On the calibration, are you calibrating on an individual home basis? Okay, so you're taking, a model, like call it a preliminary model, built your normal way, giving it energy use data for that specific project, and then finding that it's matching that same data?
Yeah, so great question. So yeah, I'll have to answer that question in two parts. One is when the homeowner answers a question, that input is used for that specific home's model. So that's a home-to-home calibration or improvement. When we get energy usage data, we get it for every home, and we sign an NDA, so it's identifiable by home address. But when we calibrate at that scale, we don't do it per home. We actually do it by vintage and by other characteristics. So we look for other characteristics, and we model, we tweak the rules that we make our energy models with. So those rules are basically based on vintage first. Secondly, they're based on age of the equipment and the efficiency of the equipment, and as it decays over time. So those are the things that we can tweak using the energy usage data. So when we calibrate at scale, it's done not at the individual level, but at that scale. There's a couple of other ways to do this too. NREL has done some work on this, so has ORNL. So there's multiple ways of doing it. We kind of came up with our own, like looking at what the others have done.
Got it. Okay, that makes more sense because you're also building something that's more widely applicable, like you're learning through this calibration process, and then can use it to help improve the accuracy of models that you don't have specific data for. I was also like, okay, if you're calibrating a building, a home to its energy use, of course it's going to be a closer match to that data. But
yep.
That makes more sense.
Thank you. And just on that point, a lot of the times energy usage data is available at scale without identifiability to a particular address. They will aggregate that data for a zip code and give that to you. And that's more easily accessible, and our methodology is compatible to that. So thank you.
I think Steve Cromer, I think you might have answered a little bit, but a subsample of all these sites have end-use metering involved even in houses. Like they've got, I forget the names of all the software, the tools you can put on the CTs on your actual building. Yeah. So a subset you could calibrate to end uses as well. And you have Google Nest and other opportunities to bring all that other operational information in.
Yeah.
Maybe not on the whole thing the way you're doing it, but on a subset to help inform the sample.
Thank you for saying that. Yes, we're working with one of the CCAs in the Bay Area, and they have a set of 28 homes that they have sub-metered extensively, and we've modeled those 28 homes on our platform as well. So they have CTs on every circuit. So they have pre and post data. So that's really great. And our initial findings, and we couldn't present that because that work isn't complete yet, but our initial findings are very encouraging that the savings that we're getting are pretty good from the modeling. There is more uncertainty. There's more spread in that data in those 28 homes. Again, just 28 homes. So we should look at that as a drop in the bucket, but still encouraging results from there. We had more? Lunchtime. Okay. Thank you, guys. Thank you for your time.
Awesome. This brings us to lunch. Hopefully our Conversation Catalyst talks gave you some ideas for what to chat about with your fellow attendees.